Hi, everyone. Welcome to this month's edition of Synapse's third Thursday webinar series. This topic, this month rather, our topic is EV rate design and how to go about it in an effective way. I'm Pat Knight, and this month I'm filling in for Bruce Bewald, who would normally be here steering along our webinar series. Our speakers today are Melissa Whited and Allison. And before we get started with the webinar itself, I want to talk about a couple of logistics. So this webinar is being recorded and will be circulated to all of the attendees. It will also be available up on YouTube via our website at synapse-energy.com/webinars. We'll probably be posting it in the next day or two, so feel free to tell all of your colleagues who couldn't make it to today's webinar that they'll be able to watch and listen in just a couple of days. All of our previous webinars are also available for free online. So take a look if you'd like to learn some more about interesting things about visualizing U.S. electric sector data, modeling congestion pricing in the transportation sector, strategic electrification, and loads of many other topics. So another logistical item that you might notice is that I'm the only one who you can hear talking. So we default all of our listeners to mute on entry, and you'll be muted throughout the webinar. However, we do want to hear from you. So if at any point you have a question about the content of what we're talking about, please go ahead and shoot an email to webinar@synapse-energy.com. You can see it at the bottom part of the screen here. I'll read them on my screen, and then I'll pose them to Melissa and Avi, either as they're talking or towards the end during the Q&A section. If you do encounter technical issues as we're talking, like you can't hear me or hear anybody else, please use the chat feature in the WebEx app. It should be on the right-hand side of your screen, and we'll tackle that and hopefully get things working for you there. So just a little bit of introduction. We are Synapse Energy Economics. We are a research and consulting firm specializing in energy, economic, and environmental topics. And basically what we do is we work for clients, mainly those in the public interest, government agencies and NGOs, conducting regulatory support, research and writing, policy analysis, electric sector and other sector modeling, all sorts of great nerdy stuff. And again, just another plug for our website. Go ahead and check it out. We post all non-confidential publications and have many open source tools that once you learn all about this interesting work through our webinars, you can do a deeper dive and learn what more there is to say about each one of these topics. So now I'll just turn things over to Melissa and Avi, who are going to start off by telling us why we care about electric vehicles.
Thanks very much, Pat. This is Melissa Whited, and thanks again for joining us today to talk about electric vehicle rate design. And so the first question that you may have is, why do we even care about electric vehicles? So quickly, I'm going to cycle through some of the main reasons. One of the key reasons cited by jurisdictions who are interested in promoting electric vehicles is that there are great emission benefits to be had by converting our gas-fueled cars to electric vehicles. And this graph shows the level of CO2 equivalent emissions annually for a traditional gas-fired car at the top, a hybrid, plug-in hybrid electric vehicle in the middle, and an electric vehicle at the bottom. And you'll see that an all-electric vehicle has about a third as much emissions, CO2 equivalent, as a traditional internal combustion engine. And this is based on national averages of the emissions from electricity. But in certain states, and especially as we move to more renewable resources, we can expect that the emissions from battery electric vehicles will be even lower in the future. So jurisdictions interested in combating climate change or just reducing emissions in general are pushing strongly for electric vehicles in many cases. And the second reason is that electric vehicles are cheaper to operate than gasoline-fired cars in all 50 states. So the fuel cost savings from driving an electric vehicle can be pretty significant, and this graph or this map shows how it varies by state depending on the cost of electricity and the cost of gas. But the annual fuel savings can be even in excess of $1,000 per year. Now, if we can bring down the upfront cost of electric vehicles, that could mean real savings for U.S. consumers. And another aspect is that electric vehicles can provide benefits back to the grid. So by increasing sales, especially when there's a lot of supply in the grid and low demand, where you don't have to increase any infrastructure to provide electricity, you have more sales over which to spread the fixed costs of the whole grid, and that can reduce rates for all customers. It can also help utilize that low-cost renewable generation that might be coming onto the system at night when there's excess generation, or in the middle of the day from solar generation. Another thing is that EVs are essentially mobile batteries. So in addition to providing the ability to do traditional demand response, simply dropping load when the system is stressed, we're also starting to see more pilots and development of the ability to provide power back to the grid when the grid needs it, and that's called V2G. So that would be power and also a host of ancillary services back to the grid. So that's great, but electric vehicles are still a pretty nascent technology. They aren't yet widespread. So the question has been asked, do we really need to do anything about EVs right now, or even really be thinking about them? And I would answer that question with a resounding yes, because of how we see electric vehicles growing over time. Since 2011, EVs have taken off rapidly, and this graph shows plug-in hybrid electric vehicles on the top and battery electric vehicles on the bottom. And they've been increasing fairly steeply, but they're still under 1 million vehicles in the United States right now. However, when we extend that trend out just 5 years, we see that there could easily be 3 times as many electric vehicles on the road and on the grid in just 5 years. And if some of the policy initiatives really get going to promote electric vehicles, that number could be even higher. So as we think about larger numbers coming onto the grid in the very near future, then we need to be thinking about what types of impacts could these vehicles have on the grid, and how can we manage this. So I'll pass it on to Avi now to talk about electric vehicle rates.
And again, I just want to emphasize that if you do have any questions about the content, please go ahead and email us at webinar@synapse-energy.com. We're happy to take any questions you might have.
Great. Thanks, Pat and Melissa. So I'm going to talk a little bit about why we're talking about rate design in this presentation. Really, actually, 2 questions. 1, why are we talking about rate design at all? And 2, why do EVs represent a type of electric use that really requires its own type of thinking about rate design? So this chart kind of helps to answer that second question. EVs matter in part because they can double a household's peak demand. On this chart, you can see a variety of household appliances up alongside some standard electric vehicle charging equipment. And what this chart shows is that a standard level 2 EV charger, commonly found in many homes that are adopting battery electric vehicles, has a much higher maximum load than really any household appliance. So it really is a different type of electricity use than most residential customers are used to. Now, as Melissa said, electric vehicle adoption remains fairly low so far throughout most of the country, but it's increasing rapidly, and it's increasing differently in different places. So already in New York, if you added up the potential demand of all electric vehicles using a level 2 charger, and if they were all to charge at the same time during peak hours, that could add about 215 megawatts to peak demand. That would be enough to offset the peak demand reduction from all energy efficiency programs in the state of New York. So we are talking about significant quantities. In California, where about half of all EVs in the country currently are located, the potential impact is even greater. It adds up to more than 2,200 megawatts. Now we're talking about several power plants worth of demand, and we're talking about approximately 5% of total system peak demand. Now again, this is kind of a worst case scenario of all electric vehicles using their level 2 charger at the same time, but it is something to think about, and it's a trend that's likely to only expand over time. Fortunately, these sorts of concerning potential aggregate demand impacts represent a problem that can easily be avoided. And that gets at the second key characteristic of electric vehicles that really differentiates them from most other types of electric uses, and that is that they represent a flexible load. What do I mean by that? Well, with most types of electricity uses, you have to draw the electricity from the grid at the same time of the energy service that you're trying to attain. Meaning, if you want to cool your house, you turn on your air conditioning unit, and it's drawing electricity from the grid at the time that you want your house to be cooled. The same goes for your toaster. If you want to warm a piece of bread, you're going to be drawing electricity from the grid at the time that you're toasting your bread. This type of logic does not apply to electric vehicles, where there's a temporal disconnect between the consumption of grid electricity and the actual use of your energy service, which in this case is locomotion, moving your car around. EV drivers don't care when their car draws electricity from the grid as long as their EV battery is charged when they want to drive. This means there's an opportunity to encourage EV drivers to charge at socially beneficial times. If they don't really care so much when they charge, you can kind of nudge them to charge at times that are better for the grid, better for society. Since EVs sit parked more than 80% of the time, there's plenty of time that you have to work with to shift charging patterns around over the course of the day. So what are some of the reasons that you might think about for using price signals to cause EV drivers to shift their charging patterns? Well, first of all, if you can get EV drivers to charge off-peak, you can avoid costly upgrades to the distribution and broader system of the grid. Second, you can encourage EVs to charge when renewable production is high, and this might help to integrate renewable resources and drive down emissions. And finally, if you can identify times when it's low cost to the system to charge an electric vehicle, you can offer rates that charge very little for EVs to charge at those times, and this low rate might encourage increased adoption of electric vehicles, which can help meet certain goals, including emission reductions, lower costs that Melissa discussed earlier. Now I'm going to pass it back to Melissa to talk a little bit more about some rate design options for electric vehicles.
Thanks. So the first and most common type of rate design for electric vehicles is time of use rates. And under time of use pricing, you might have a load shape like this blue graph. And this is actually from Avista Utilities in Washington State, where this is the average load profile for their electric vehicle drivers without a different price signal. And you see a lot of those drivers are plugging in right when they get home from work, a little bit after 5 p.m. And that can contribute to new peaks on the system or exacerbate peaks. So you could layer on top a price signal that has different prices for different times of the day. And in this example, the price is highest then for those peak hours, encouraging the customers then to shift their charging to the middle of the night or to other periods when the price is low. The second option is critical peak pricing, which is very similar to time of use pricing, except it's a much higher price, and it's only applied a few times a year during those critical peak events where the system is really stressed, and you need to provide a very strong signal for customers not to charge their electric vehicles or do other things using electricity during those hours. So this critical peak price, for example, is slightly lower than the flat rate for most of the year, but then for those few years, it might be 5 or even 10 times higher than the flat rate. The third option is a demand charge. A demand charge is generally applied to a customer's maximum demand during the month, regardless of when that occurs. So oftentimes it's tied to a single hour. And in this graph, we have the customer's hypothetical load over the course of a month, and there's a single hour in which the demand reached 7 kilowatts. So if the demand charge was applied to that of $5 per kilowatt, then that customer's monthly bill would show a demand charge of $35. And then option 4 is a little bit more advanced, and this is hourly pricing, where the prices and the time periods are not set in advance, but they just vary based on system conditions and market conditions. So the price just tracks whatever the market is, and this has actually been in place for Commonwealth Edison, as well as San Diego Gas and Electric have a pilot, VGI rate, that uses some form of hourly pricing. The graph here shows Commonwealth Edison's program and their typical prices, hourly prices during the summer and during the fall, winter, and spring. But this is just typical. It can really change from day to day, from hour to hour, and they're generally day-ahead prices, so customers have some idea of what the price is going to be the next day. But other than day-ahead, you don't really know what the price is going to be next week. And finally, for any of these options, you can offer them as a whole house rate or an EV-only rate. The whole house rate would apply to the EV as well as all the other aspects of household electricity use. And the EV-only rate would only apply to the electric vehicle charging itself. So I'll pass it back to Avi to talk about what we've seen when some of these rates have been applied.
So the main piece of evidence we've seen from a variety of experiences with time-varying rates is that these time-varying rates work. They achieve their central objective of causing electric vehicle customers to shift their charging patterns and their electricity consumption. So here we have a chart from a pilot conducted by Baltimore Gas and Electric, where they took a sample of customers who owned electric vehicles, and they looked at their charging patterns and overall consumption patterns on a standard rate, and then they put those customers onto a whole house time of use rate and saw how the consumption patterns changed. And what you can see on this chart is that initially on the standard rates, these customers tended to have their peak consumption occur during late afternoon and evening hours, which are typically going to be your system peak hours. So potentially the hours that were imposing costs on the grid. However, when these customers were shifted on the whole house time of use rate, where they are penalized for charging during system peak hours, they shifted their consumption later into the late evening and overnight hours, thereby reducing costs on the grid and achieving the objective of shifting peaks. Here on this next slide, we have an example from San Diego Gas and Electric, which has an EV-only time of use rate. And you can see that this rate has been very effective, extraordinarily effective really, at convincing customers to charge during off-peak hours. On the SDG&E system, they chose to select these super off-peak hours between midnight and 5 a.m. And you can see that almost all charging tends to happen during those hours, and very little charging happens during the peak hours of the evening weekdays during the summer. Other utilities in California have had similar experiences with EV-only time of use rates. Here we can see that for Pacific Gas and Electric and Southern California Edison, about 90% of all charging on these EV TOU rates happens during off-peak periods. Again, those periods of lower cost. Finally, one other lesson that we've taken away from California's experience primarily is that EV rates can help to successfully mitigate any grid impacts. Again, about half of all these in the country are located in California. So if you were going to expect to see grid impacts from EVs anywhere, you would expect them to be in California. However, very few California electric vehicles have required any distribution system upgrade costs. This chart shows that only about 0.2% of electric vehicles have required any upgrades in California. And the total upgrade costs from these electric vehicles have amounted to less than 1/100% of all distribution capital costs. So really a minuscule number at the end of the day. Next, I'm going to talk a little bit about some design considerations for creating electric vehicle rates. Starting with, once you've decided to create a time of use rate targeted at electric vehicles, how do you go about determining your time of use periods? And the way to think about this is to try to figure out for a given utility in a given year, you want to figure out what are the time periods when costs are highest to the system and what are the time periods when costs are lowest. And one method for doing this is to add up various component marginal costs, including energy costs, generation capacity costs, and distribution capacity costs, to create an aggregate sort of heat map that evaluates the cost to the system across various hours and various times of the year. So in these heat maps, we have on the horizontal axis the hours of the day, ranging from the first hour to the 24th, and then running vertically, we have the months of the year, January through December. And what we see from these heat maps is that for this utility anyway, the highest cost hours, the hours that impose the most costs on the grid, tend to happen during the late afternoon and evening hours, especially during the summer months. The lowest cost hours tend to come actually during the middle of the day in the spring months for this utility, basically because those months tend to have mild weather paired with fairly high production from renewable energy sources that have zero marginal costs. One important note is that time of use periods don't need to be the same across various customer classes. So for residential customers, often residential circuits will have their local peaks come during the same types of hours as the system peaks, that is, during late afternoon and early evening when people come home from work. For commercial circuits, the story can be different. Often those circuits tend to peak during the middle of the day when businesses are operating. So there's no need for time of use periods to be the same across these different customer classes. One concern that sometimes gets raised, maybe especially with respect to the use of time of use rates, is the fear that they may lead to some new sort of peak creation at the local level. That customers will respond so well to these rates that they'll all charge at the same time right when this off-peak period starts, and this will create this new form of peak clustering that can lead to distribution system costs. One thing that we've found is that, first of all, so far this doesn't seem to be a major problem, but second of all, the design of your time of use periods can mitigate this issue. So this chart shows that the longer you enable your off-peak period to be, the lower the level of clustering of peaks, and the lower the concern about new distribution system peaks. Basically, the finding is that longer off-peak periods, as you might expect, increase the diversity of charging times. In addition, there's the possibility that in the future, more advanced utility direct control programs could be used to mitigate any clustering issues by allowing the utility to cycle electric vehicles charging on and off to make sure that that there's not too many vehicles charging at the exact same time, even during off-peak hours. Now Melissa is going to tell us a little bit more about rate design considerations specific to residential customers.
So when it comes to residential customers, one key thing to keep in mind is that while we might be able to design the perfect rates that perfectly reflect system conditions, we also need to keep it simple, understandable, and predictable, especially for residential customers. For many customers, time of use rates are fairly new, so going beyond time of use rates might not be the best thing to do, especially in these early years. Time of use rates are pretty easily understandable, as you can see in this graphic from Con Ed in New York, their Smart Charge Rewards program. It's just a simple graphic that just says don't charge between 2 p.m. and 6 p.m. And that's also compatible with a lot of set it and forget it technologies that allows customers to simply program their electric vehicle to charge at night. And they don't have to worry about what the actual price is at 4 a.m. versus 2 a.m. Now, when you're thinking about implementing some form of rate for electric vehicles, I mentioned that you need to consider whether it should be an EV-only rate or a whole house rate. And offering a separately metered EV rate might be beneficial to getting customers to enroll, because some customers feel more in control of their electric vehicle charging than the rest of their house electricity use. So they might be more comfortable simply enrolling their electric vehicle on a time of use rate, whereas they're not so sure about when they actually use electricity in the rest of their house. So for that reason, customers may prefer an EV-only rate. However, such rates require that there be some form of sub-metering technology, and that can be a whole new second meter to measure the electric vehicle separately, or a standalone sub-meter, an in-car device, or a sub-meter that's integrated into the Level 2 EVSE, electric vehicle supply equipment. Unfortunately, at the moment, we see that a lot of these technologies involve relatively high upfront costs and ongoing data management fees for communicating all that data from the electric vehicle's charging back to the utility for billing purposes. We're seeing that these technologies are advancing quickly, and perhaps very soon in the future, we will have developed a level of comfort with the various types of smart meter technologies that can also provide load disaggregation and other communication systems that can provide the data back to the utility in a more cost-effective way.
Melissa, I'm wondering if you could talk a little bit more about these sort of sub-metering technologies and give us some sense of the magnitude of the costs or benefits that are associated with some of these. I know that there's a lot of different options out there right now, and it seems like there's a way to go before we, as you know, a society with electric vehicles sort of settles on one as the best option, or has a suite of options. But I'm just wondering if you could talk a little bit about the costs of these, as they stand right now, at least.
Sure. So a lot of these have an upfront cost of several $100s. The simpler ones, maybe just a couple $100s. The more advanced EVSE Level 2 equipment may run you $600, depending on the type that's chosen. But in addition to that upfront cost, you have the data management fees. And I believe in the California sub-metering pilots, they were seeing about $18 per month for the data management and communications needed to get that data back to the utilities. As I mentioned, this may not be needed in the future as we develop more advanced metering technologies and other methods of sub-metering. And all of these sub-metering options provide different capabilities as well. The one here on the bottom left of the slide, that's a little plug-in into the dashboard of the electric vehicle. That's the Fleet Karma device. And the Fleet Karma device is pretty cool because it goes with you wherever your car is. It doesn't just sit in your garage. So it can actually tell when you're charging when you're away from home as well. Of course, that's raised some concerns about privacy and the GIS information that's captured. We know that information is confidential, but still it may not be embraced by customers because of that. Another aspect to consider when implementing residential electric vehicle rates is customer inertia. We've seen this with all types of customers in the past, or EV and non-EV residential customers, that customers just tend to stay on the rates that they're already on. And there's a lot of just resistance to taking the time and calling the electric company and enrolling in a new rate and learning about it. So on the right here is a graph from a bunch of smart grid investment grant programs that implemented some form of time-varying rate. And they looked at whether or how many customers would actually opt into the program versus opting out. And opting out means that you're defaulted into the time of use program and you have to actively opt out. Under opt-out, we saw enrollments on average of over 90%. That means that most customers, were defaulted onto the time of use rate and just stayed on it. In terms of opt-in, which is the blue bar there, the enrollment levels are much lower. well below 20%. In terms of retention, the number of customers that actually stayed, the vast majority of opt-out customers who were defaulted onto the time of use rate stayed on the rate. But opt-in customers, of course, you would also expect them to stay on the rate since they chose it. But those results were very similar to opt-out. So perhaps eventually we'll get to the point where we just default customers with electric vehicles into the rate, into some time of use rate. At the moment, that's not very practical, and we may want to get some more comfort with time of use rates before defaulting customers onto it, although I will mention that California is moving to default time of use rates for all residential customers. So in the meantime, though, if you're considering an opt-in framework, you'll want to be aware that even for electric vehicle customers, you're probably going to get relatively low opt-in rates unless you pair it with a lot of education and outreach and incentives for customers, such as customer enrollment bonuses and training at the dealership to inform customers of these rates.
And Melissa, we've gotten a question in that's actually just about what you were just talking about, the idea behind necessary education for time-varying rates. Time-varying rates have been around for a while across the country, but generally they are not widely adopted by most consumers. And I know that there's been some concerns about different segments of the population and how they might learn to understand time of use rates, or whether it might negatively affect them in some way. So I don't know if you have any information to say about that.
Yeah, some utilities have price guarantee programs when customers are defaulted into a rate, or even if customers opt into a time of use rate and are not really sure about whether it's going to be good for them. A price guarantee program will allow customers to try it out with basically no negative impact. What generally happens is that the utility takes the customer's bills at the end of the year under the time of use rate and compares them to what the customer's bills would have been under just the standard rate. And if the customer's bills were higher under the time of use rate, then they can leave the time of use rate and actually get refunded for whatever they paid above what they would have paid on the standard rate. So that's a great option. It's been implemented by a number of different utilities, including in New York and Minnesota, for encouraging customers to opt in and try it out, see if they like it. And that can also be a good protection measure for defaulting customers who may not have the ability to shift load. I mentioned customer incentives, and utilities have taken a number of approaches to even trying to get information on how many EV drivers they have in their territory. Electric utilities don't often know whether a customer has bought an electric vehicle unless the customer tells them. So this example is from Salt River Project, where they're offering customers $50 simply to enroll with SRP, let them know that they have an electric vehicle. So that's one type of incentive. Other types of incentives can be provided by the dealer to, let your utility know that you have an electric vehicle, or enroll in a time of use rate. So other types of utility outreach can include bill inserts about electric vehicle rates, website information, and lots of other types of outreach programs and campaigns to educate customers on time of use rates in electric vehicles. And I mentioned dealership training. That's really important for ensuring that the people who are actually interacting with customers who are potential buyers of electric vehicles know what it might cost to charge that electric vehicle and what the electric utilities offer as rate options, especially if it's going to reduce the cost of charging the electric vehicle. And one study found that only about 19% of salespeople give reasonably accurate answers about how much it's going to cost to charge an electric vehicle.
So Melissa, if a person who's going into an electric vehicle dealership or into an any car dealership and looking to buy an electric vehicle and they're not getting great information from the salesperson necessarily about how much it costs to charge an EV versus how much it might cost them to buy a regular car and fuel that instead. How might they learn about that? What are the options that consumers have?
Yeah, so a number of utilities have this information on their website where you can actually go on and put in the type of electric vehicle that you're considering, how many miles per day you're going to drive, and you can compare different rate options, so charging on a standard rate or charging on a time of use rate, and how the time of use rate could really reduce your bill and what it would actually cost, if you decide to charge overnight or during the off-peak hours. So that's one option. I think that, this is a real opportunity for utilities to step forward and ensure that that information is out there and easily accessible and very, very easy to use. These calculators online, I think that they're great because they really tailor the information to each customer's unique situation. And in some jurisdictions, we see performance incentive mechanisms for utilities being implemented, sometimes to address electric vehicles as well. And those performance incentive mechanisms for the utilities could actually target enrollment of electric vehicle drivers on time-of-use rates as just another step to encourage utilities to really get out there and provide this information and actively enroll customers on the EV rate. Now, for public fast charging especially, and workplace charging, there are many of the same types of considerations to bear in mind, but some other nuances that are unique to this type of charging. Most commercial and large customer rates have a demand charge. As I mentioned, that's usually a charge based on the customer's maximum kilowatt demand during the month. For DC fast chargers, especially in these early years of electric vehicle adoption, typically they don't get used very frequently, but their demand can be very high. And this can mean that the economics of operating and installing one of these DC fast chargers doesn't pencil out with a demand charge. And that's problematic because it's a bit of a chicken and egg problem here. If you don't have the DC fast chargers to support more EVs, then you're not going to get more EVs. If you don't have a lot of EVs using the DC fast chargers, then it's really hard to recoup the cost of installing and operating these DC fast chargers. So just as an example, let's consider one DC fast charger that has two 50-kilowatt ports. So it's the potential for having 100 kilowatt demand if there were two customers charging their cars at the same time. So in this table here, the top row here of the high case it has a customer charge of $70, energy charge of 8 cents per kilowatt hour, and a demand charge of $20 per kilowatt. If that DC fast charger did hit that 100 kilowatt demand, but it only had 16 charging sessions per month, that DC fast charger would be assessed an annual bill of over $25,000 with an average cost per charging session of $133. And even if you double it and you assume that at least two people are charging at that station every day, the annual bill is almost $28,000 with the cost per session of $39. So that's very difficult to have the economics pencil out with those types of cost per charging session. I'm sure that the drivers who are using the DC fast chargers aren't paying $133 per session. So in this case, the fast charger would have no opportunity to recoup its costs. And this is a similar case even under a lower demand charge of $6 per kilowatt. There, the cost per session is $46, assuming 16 charging sessions per month, or $14 per session of 60 charging sessions per month. So to address this, because a lot of jurisdictions recognize that we do need more DC fast charging equipment to support higher EV penetration, some utilities and jurisdictions are reducing that demand charge or even eliminating it, at least temporarily. And that also enables these DC fast charging owners to more easily pass on the cost to the customers that are using them. And it's somewhat similar for small and medium commercial customers who may have a row of level 2 chargers for their employees or for their customers. The demand charges associated with the use of that charging equipment, even if it's level 2, can add significant costs to the host customer's bill. So again, our recommendation here is to think about removing or at least reducing demand charges, at least temporarily, until we get beyond this chicken or egg problem and see higher penetrations of electric vehicles capable of supporting the infrastructure. And another recommendation that we make is to minimize the variability of these types of rates for DC fast charging hosts, especially across utility service areas. If you have a company and you want to operate a suite of DC fast chargers throughout a state, for example, it can be very difficult to figure out the economics when you have multiple utilities charging completely different rate structures. And now I'd like to just sum up our discussion so far with some key takeaways. So first, as we discussed in the beginning, EVs can provide a host of benefits to grid and society, from emissions reductions, fuel cost reductions, and reducing the cost of electricity or rates to all customers by increasing sales and spreading those sales over, spreading the fixed costs over those increased sales. And even in California, where we have about half of the electric vehicles currently, the grid impacts from EVs so far have been relatively minor. But as we showed, EVs are gaining and growing very quickly, so we want to make sure to plan for the future and avoid the potential for grid impacts. Time-varying rates are a great way to do that. They can help avoid those grid upgrades and also encourage electric vehicle adoption by providing lower-cost ways to charge. And for residential customers, when implementing time-varying rates, it's important to keep it simple. Time-of-use rates provide a good combination of simplicity as well as relatively efficient price signals. And as technology improves and we have more options to automatically control our end uses, including electric vehicles, but possibly also other appliances in the house, more complex rates can be considered. When moving to any rate, we'll need to include education and outreach, and to combat customer inertia by taking active steps to enroll customers and make sure that they're informed. And for public and workplace charging, demand charges are a key barrier, especially in these early years. So we've talked at a high level about many of the main lessons about electric vehicle rates, but there's a lot more to read about, a lot more detail out there. Synapse has done quite a bit of work on this for Natural Resources Defense Council, and we have a number of publications related to those projects on our website. So one of those publications is a plug for effective EV rates. Then there's electric vehicles are still not crashing the grid, which is an update of some of the analysis that we've done in California. And we also have testimony related to electric vehicle rates on our website, where you can go and download that. And now I'll turn it back, open up for questions.
Yeah. So thanks to Avi and Melissa. A lot of really interesting information on a sort of cutting-edge topic. So we've been getting in a large number of questions, but we should have time to hopefully get to many of them. If you have a question, again, please email it to webinar@synapse-energy.com. That's the link there on the screen, and I'm happy to read it out loud here to Avi and Melissa. So I want to start off just by asking a question about sort of smart technology that is embedded in today's electric vehicles. One of the earlier charts, I believe, that Avi showed indicated that electric vehicles have the potential to pull up to 7 kilowatts or so at any given point in order to charge their vehicle's batteries. But I'm wondering if you could talk a little bit more about the technology that many electric vehicles have built into them that allow them to be smarter, I guess, about when they're pulling power and how all that works.
Yeah, so technology is evolving rapidly, and it does vary by vehicle. A lot of the new technologies that we're starting to get familiar with and evolve are related to vehicle-to-grid integration, and SDG&E is one of the leaders here in terms of advancing more complex rate design that can then pair with technology to charge very smart. Their vehicle-to-grid integration rate uses hourly pricing, and they have an app where you can set it so that it only charges during the lowest cost hours. And that hourly pricing, again, can vary from hour to hour. So you set up the app, and it can just automate the charging for you so that you're really taking advantage of the lowest cost hours.
So we've been talking a lot about California, and I think that's because half of the electric vehicles today are in California. But I'm wondering if there's any specifics you can give about EV time of use rates that have been implemented outside of California, or areas that are thinking about shifting towards these either EV-specific rates or general time of use rates, and also whether there are sort of cookie-cutter time of use rates that utilities can rely on in order to make their new rate structures for electric vehicles.
Maybe I'll answer the first part of that and pass it over to Avi for the second. There are a lot of electric utilities right now that have time of use rates available. Some of them are specifically targeted to EVs, but a lot of them are simply available to all residential customers. There are a number of utilities that have implemented the EV-only rates, including Austin Electric, Dominion Power in Virginia, Georgia Power, and typically those rates will include some super off-peak component that you might not see with a standard time of use rate. And those rates may have an option to do an EV-only rate, only apply it to the EV as opposed to the whole house. So I think the Smart Electric Power Alliance released a study where they had 47 different utilities that were offering some form of time of use rate for EVs. And some of the rates even go beyond, time of use rate or hourly pricing. I think Braintree Electric here in Massachusetts offers an $8 credit just for charging off-peak. And Austin Electric offers, I think it's free charging up to a certain number of hours for charging off-peak. So there's a lot of variety in the types of rate options out there right now.
Yeah, and just to add to that a little bit, we've been recently looking at some new proposals from utilities in New York State, which were all required to show that they had some sort of time-varying rate oriented towards electric vehicles. It's interesting just to see the variety within those utilities located in New York. Some of them are now offering separate metered EV-only rates. Some of them are sticking with their whole house time of use rates. Some of them are offering time of use rates that have really high ratios of off-peak to on-peak charging prices, up above 10 to 1, whereas others are down more like a ratio of 2 to 1 between those on-peak prices and off-peak prices. Some of them, so in some states where there's retail competition for energy supply, there can be differences among utilities in terms of whether they offer time of use rate only for the delivery charge or also for their standard supply charge for utilities that stay on the standard service with their local distribution utility. So really a lot of variety out there. And there really is no single cookie-cutter approach that exists, or I think that we would recommend, especially for things like figuring out your time of use windows, when your on-peak period should be and when your off-peak period should be. That's really going to vary a lot depending on geographic conditions, depending on system variances in terms of the number of renewables that are on your system, what time your local renewables tend to peak, the type of weather you tend to get in your region. And those factors, in particular, when the low-cost renewables are online and how many of them are online, are going to change over time. So it's important, even within a single geography, to revisit your rates every now and again and not to treat them as some stock thing that remains constant over time.
Yeah, I think that's one of the more interesting things about EV time of use rates is the idea that the time of use rate that might be most suitable for a number of policy reasons today might not necessarily be the best rate 5 years from now or 10 years from now.
Yeah.
Another topic I'm hoping that you can talk a little bit about is the issue of cross-subsidization and what happens when there are a significant number of EV customers and what the impact is on customers who don't have EVs. I'm also curious about the impact of cross-subsidization on sort of larger or public charging infrastructure where, say, demand charges are reduced in order to encourage adoption, but obviously somebody has to pay for that somewhere, and how would that work?
Sure. Well, there's a lot of aspects that go into rate design. One of them is ensuring that you have efficient price signals so that customers are paying for the cost that they impose on the grid, but are also faced with a marginal cost that reflects, expansion of service. And as long as your prices are above marginal cost, there can be a real benefit to increasing sales without necessarily having to increase much at all the cost of infrastructure out there to provide those sales. And that's what we're looking at here with smart charging. If you can simply locate the charging during those hours when you're off-peak, then there should be very little additional infrastructure costs related to integrating these EVs. But at the same time, you're increasing sales a fair amount, which can reduce rates for all customers, and also making use of those renewable energy sources that are providing a lot of electricity in the middle of the night or in the middle of the day. So, with that borne in mind, there could be some cross-subsidization in the very strict sense of cost causation, but I think that can be primarily avoided through implementing these smart charging rate structures. And another aspect is the avoidance of emissions and the other benefits that electric vehicles can provide. So in that sense, if that's not quantified or monetized, then it's not clear that electric vehicles, that there is any cross-subsidization, because you really have to look at the whole suite of benefits that they can provide to the grid. I think also as technology improves and we see electric vehicles providing more services back to the grid, becoming virtual power plants, we may see more opportunities to actually reduce costs on the grid by providing lower cost services. So I think it's an empirical question overall, but I don't think, at least to me at this point, it's not one that I'm terribly worried about, because I think that electric vehicles can be integrated in a way that largely provides benefits for all customers.
So what's the solution then for public chargers or highway chargers that don't necessarily have control over when people want to use them? Basically, they're going to provide electricity when people drive up to them, and they can't shift power, so to speak.
Sure. So there's that actual cost of first installing the infrastructure, and we encourage utilities to work with the charging equipment providers to ensure that first they're located in places where they're not going to add a lot of additional cost to the grid. But secondly, we've advocated in California for simple time of use rates for those DC fast charging equipment, because customers understand that there are time of use rates throughout, at home. I think that they'll be also amenable to not charging during the peak periods. And again, technology, the ability to control how customers charge, perhaps you really need to charge during a peak period, but you agree to charge at a slower rate or something that's not going to put quite as much strain on the grid. So I think that we'll see lots of opportunities for mitigating those types of problems going forward, and I think we'll see time of use rates become more widespread, even at DC fast charging.
So we've talked a little bit about the technology options that exist today for measuring the consumption of electricity by EVs themselves separate from the meter that people already have in their homes. What I'm wondering is what sort of quality do these sub-metering options have to have? Do they have to be utility grade? How does that play out in terms of making sure that the data that's being recorded and essentially converted into charges to the customer, how is that going to all fit together with these new pieces of technology?
Well, first of all, I do want to say that California has been on the forefront of this for quite a while, and they've been making a lot of headway. Thank you, California, for being the guinea pig for all of this. They tried out a variety of different sub-metering technologies. Had a few bumps in the road at first. They're now on phase 2, and I think what they're seeing is that generally the quality is very good once you get around some of the communications issues. So I think that the quality isn't really the concern going forward. Yes, we are ironing out some kinks as we move forward with this technology right now, but I think that's quickly progressing. And yes, they need to be, accurate enough to provide, the right data back to the utility. But keep in mind, these are also sub-meters, so the total amount of electricity being sold to the premise is going to be the same. And I think with the sub-metering technology, very small deviations, 1% or less, it's very, very minimal. And we actually see utility revenue grade meters also have some issues with, not perfectly capturing sales. So I think that, in general, we're moving past that problem, and the technology is there.
Great. So I think we're going to be wrapping things up here since we're rapidly running out of time. So thanks to everybody for joining. And if you have any other questions about this topic or questions about other topics or other ideas for future webinars, please reach out to Melissa, Avi, or I, or to the webinar at synapse-energy.com email address. We always like hearing from people and hearing what you're interested in and tailoring the next talk to that topic. So remember to check out this webinar. It will be posted later this week at synapse-energy.com/webinars. And we look forward to you joining us at the next third Thursday webinar to be held on May 17th. So mark your calendars. We don't have a topic yet, but we'll be here a month from today. So thanks, everybody, and we'll talk to you soon.
Thank you.